All right. So what we're going to do now is this jumping lab. And this is our first example of a lab that actually does have an objective and a hypothesis. We're going to have a number of these as we go through the semester. Um, do we really care about the relationship between the body and how high someone can jump? That's kind of besides the point. This is more of an exercise in the process of how do you kind of form the question? How do you set up the experiment? How do you analyze the data? How do you then look to see if your hypothesis is supported or not? So the first part of any good experimental inquiry is having a well-formed question, like really knowing exactly what is the point? What are we trying to figure out? Because unless you do that, you're not going to really know how to create an experiment to answer your question. You're not going to have the ability to know, like if you found your answer, if you weren't exactly sure what you were asking in the first place. So having a good objective is really important. In looking at what people have turned in, there's a huge range. I think it is going to be worth spending a few moments looking to see what different people have turned in terms of their hypotheses and objectives, just so you can see what looks good and what doesn't look so good. I think this will work. Right, here is somebody's objective and hypothesis, and it's simple, but it's nice. How is the subject's height, weight, and or calf circumference related to how, it should, how high they can vertically jump if you were going to be more explicit. But basically, the objective is very clear, very specific. It has the actual variables we're actually measuring, and it's just a simple question. How are they related, or was there a correlation? Hypothesis also deals with the actual things we're looking at. Heavier, which I'm assuming means larger weight, will have lower jumps. And why? Because they're going to have to, fight more against gravity. The more you weigh, the more you have to fight gravity to jump. So again, it's not complicated, but it's clean and it's to the point and is taking care of, here's the variable she thinks is going to be worth, going to be important to look at and why. And then sources of variability, genetics, injury, energy levels, attitude. These are all things that very likely could have an effect on the jumping. And notice there are also things we're not measuring. A lot of people put sources of variability like height or BMI. It's like, no, we're actually looking at those. Those aren't variables, not sources of variability. They're actually things we're controlling for and looking at very specifically. So, you look at this here, it's very like kind of streamlined, but it's got everything it needs and it's done well. This objective hypothesis, source of variability doesn't have to be super complicated. In fact, the more you can really just hone in on what is the key thing, the clearer you've just stated things, the less confusing things are.
Have you finished reviewing those?
Some of them, not all of them.
Okay, because I'm A and I haven't gotten a review on mine yet.
Yeah, so I haven't got to all of them yet because because people start handing more, revising them, and I look at them, but then I don't get to everyone before it's time to check in with everybody again with Zoom. So I will give you feedback, but I apologize if you haven't gotten personal feedback yet. This one here, objective, does one, so again, the grammar just should be one's weight, but again, does one's weight, height, maximum calf circumference affect how high you can jump? Again, that's a nice statement of the objective. Sources of variability, again, training would be important, injuries, level of energy. Hypothesis, heavier people. Again, this person has a very similar thing. Here's one that misses the mark. Objective, determine if body parts can be utilized to predict the ability to do an activity. It's not bringing in the independent variables at all. It's not mentioning, we're specifically looking at people's height, weight, and or calf circumference. And this is not bringing that in at all. Their hypothesis, the hypothesis here, they're bringing in BMI, even though they didn't even mention BMI up here. And then there's no why. Like, why would BMI be helpful in predicting? They don't mention. And then also, then they bring in shoe wear, which isn't one of our variables. It would probably be a source of variability, but it's definitely not one of the independent variables that we're looking at. So this hypothesis here, it brings in one thing we are looking at, but doesn't give us a why. And then it brings in another thing, which we're not even looking at as a specific variable. And then under their sources of variability, they include BMI and height, which actually are things we actually are measuring. They're not the sources of variability. Attire would be. So just kind of putting that out there. This is kind of an example of missing on the objective. The objective needs to have the independent and dependent variables specifically mentioned. Hypothesis also has to specifically deal with variables we're measuring and include a why. Let's see. This one here. Purpose of a jump allows to gather data, predictability done vertically, can height, weight. So this is okay, although it gets a little like wordy. It could just be more concise. Students who are healthy. So this would, health here, the reason I put this in is their hypothesis is not actually directly using a variable, healthy. We're not measuring healthy. So what does that mean? So if you are going to, if you mean healthy BMI, you have to say that. If you could say, I think subjects who have BMI between 18 and 25, which is considered the healthy range, will have better jumps than the unhealthy BMI because they're going to have a better ratio of muscle mass to fat. So they'll have strength to push them off the ground and less weight to push or something. But doing something more vague, like healthy people will be able to do it better, that's too vague. Okay, there's that. Let's see this one. Again, this is just too vague. The objective, correlation between the vertical jump and one's body measurement. You need to be specific. We're looking specifically at their height and their weight and their calf circumference. And then hypothesis, if one's vertical jump is higher, then their body measurements will be larger because there is more power with weight. Like, I don't even know what that means. Like which body measurements will be larger and more power with weight of what? Like this is just too, you need to be more explicit, more specific. So is this making it clear? Because I'd say like half the class seems like they really understood the idea behind the objective and the hypothesis, and about half the class seems pretty lost. In this process of coming up with a objective and a hypothesis is going to be a recurring theme through the entire semester, through all our labs, through all of our hypothesis-driven labs. So if you have questions or I gave you feedback and you're still not sure, it's going to be iterative. Iterative meaning like, you'll do it, I'll send you some feedback, you'll do it again, I'll say that's better, but still, and I will also say, I know that especially if it's something you're not as comfortable with or used to, it can be, so we're uncomfortable. I do things that I'm not used to doing or I'm not good at, and it doesn't feel good to like suck at something, I can say. And so the whole point of being in this class though is like, if you're great at doing this, you probably should be in another class. So it's part of the nature of being kind of on your growing edge of where you're learning new skills that, you make mistakes or there's, I do my best to do feedback in a way that's not like making you feel bad, but I know sometimes just getting negative feedback feels bad. So do know that especially in the beginning, there'll probably be a lot of these comments like, wait a second, you need to like have a reason here, or like you're missing the independent variables here. And that's part of the process. That's part of how this works. So I don't want people to just shut down, this first lab and you're getting like this feedback, you're doing it wrong. People like, then screw it, I'm not going to do it at all. Just like I want it to be a process where you kind of start realizing, oh, I see how this goes, and you get more and more like kind of sophisticated in just seeing what exactly is the question, what are the variables we're looking at, what can we responsibly say we're measuring, what are we not exactly measuring. That's another thing in a lot of scientific experiments, what you're interested in and what you're actually measuring are different, because you can't measure what you really are interested in. Like in this lab, it would be great if you could measure muscle mass in your legs, because that probably has a lot to do with things. But given our, what we have in this class, we can't do it. So we're measuring calf circumference. But calf circumference, maybe it's related to muscle mass and maybe it's fat. Who knows? What things could we do to try to feel more confident that a larger calf actually is larger muscles rather than just more obese?
Have them flex.
Given the things that we're given, the actual independent variables and different indexes that we are looking at, what could we do to try to look at their calf, but then think about whether it's more likely due to fat or due to obesity, fat or due to muscle.
Observation? Maybe?
No, so again, think about just the measurements we already have. I meant to turn this scroll off. Hold on, let me do that.
Reference it to our BMI.
Yeah, so think about BMI. BMI is this thing, there's the healthy range where you tend to have a healthier proportion of muscle to fat in your body if your BMI is between 18 and 25, or you can be more obese if you're above 25, or I guess it's overweight from 25 to 30, obese from 30 above. So we could look at if somebody has a healthy BMI, then calf circumference is probably more likely actually related to muscle in their calf. If we have a large BMI above 25, then a larger calf is more likely to be due to having like more kind of adipose rather than more muscle. Right, so we can play around like that. Like maybe calf circumference is correlated with jumping, but only in people with healthy BMI, because in that case, a larger calf is more likely to be due to larger muscles for launching versus just larger calf because you've got more adipose. So that you can play around like that. So blah, blah, blah. Any questions about that? So I'm going to go back to go to modules. Hold on a sec. La, la, la. Modules. Okay. I'm going to share. I'm going to go down to labs. Again, chemistry review lab. You still got like a week or so to get that turned in, week and a half. So just at some point, don't forget that it's still on your plate. Everybody did the jumping pre-lab. So now we're doing the jumping lab. Before we actually start looking at the jumping lab, I have a few more of these various and sundry things. One, we're not going to read this whole all the way through, but it's a poem that I think is really kind of nice and useful. A Love Letter by Nanao Sakake. Part of the reason I have this here for you to read is this idea of orders of magnitude and just thinking about, especially now that we've just talking about atoms and ions, and now we're going to be talking about the whole organism. If I am looking at an atom, it's about 10 to the minus 10th meters. That's called 1 angstrom. Like the diameter of an atom. When I'm drawing like, oh, here's an Na or whatever, I'm talking about something that small. 1 over that many meters. Super dinky, right? Later on, we'll be talking about like the heart. The heart, that's about maybe 10 to, 10 to the minus, it's about a decimeter, 10 to the minus 1 meter, 1/10 of a meter. Are we talking about actual, just the human? It's about 2 meters tall or so. So the difference, but then I'm going to be drawing things on the board. I'll be drawing things like, oh, here's some cell and here's some sodium ions going in and out. And I'll be drawing, oh, here's the heart and there's blood moving around. And I'll be drawing them all on the board and they all look about the same size in terms of a drawing. But I want people to keep in mind that the scales that we're talking about are so radically different. 10 to the minus 10th for these atoms, basically 1. So we're talking about 10 orders of magnitude difference from what we're just drawing on the board. It's going to be 10 powers of 10 difference between drawing little atoms going in across a membrane to drawing organs and organ systems. So the reason why I have this little poem in here for you, actually, I want to see the poem. That's better. Within a circle 1 meter, you sit and pray and sing. So the whole point of this, instead of going littler, which is harder, I think it's easier to think about getting larger. So we're going to start, instead of at 1 angstrom, we're going to start with 1 meter, which is basically the little circle you're standing in real life. Within a shelter, 10 meters large, you sleep well, rain sounds a lullaby. That's your room. 10 meters, 1 order of magnitude. You know, we keep going. A field 100 meters large, raise rice and goats, 2 orders of magnitude. Within a valley, 1,000 meters, gather firewood, water wild vegetables. You know, 1,000 meters. What's another word for 1,000 meters?
A kilometer?
A kilometer. So we have 3 orders of magnitude here. We've gone from a little circle we're standing in to about 2/3 of a mile. You know, a circle 10,000 kilometers large, circle 10,000 kilometers large, walking somewhere on Earth. In fact, the definition of the meter originally was the distance from the equator to the pole is 10,000 kilometers. So here, 10,000 kilometers, we're talking about, that's 10 to the 7th, 7 orders of magnitude. So 7 orders of magnitude, which is nowhere, not near 10 yet. You've gone from a circle you're standing into the entire freaking planet. And we're still not at the range of orders of magnitude we're looking at in the class. We keep getting bigger. Within a circle, 100,000 kilometer large, swimming in the sea of shooting stars. Within a circle, 1,000,000 kilometers large, and the spaced out yellow mustard blossoms. Within a circle, 10 billion kilometers large. So 10 billion kilometers, that is all. Now we're finally at 10 to the 10th. This is 10 orders of magnitude. This is the same difference between the atom and your body in terms of size. You'll pop far out of the solar system mandala, or mandala, however you say it. Kind of just giving you this idea that when we are drawing little pictures of a cell with little ions going in and out of the cell, and then here's drawing a picture of a person with their, you know, with their heart and the blood going up and doing different things in their brain. The difference between this and this is the same difference between you standing in a little circle and, you know, the sun and all the planets and being far outside of the solar system. You know, just to give you a sense, like, I am going to be freely talking about ions moving in and out of cells, but remember that it's happening on some crazy, tiny, infinitesimally small scale. But still, it's going to be useful in understanding what's happening in the entire organism as well. But just kind of, I have that poem in there because, one, it's pretty, and one is I think it really does kind of give you a sense of orders of magnitude in a kind of fun way. The other thing that you can look at on your own, but I'll just mention briefly, is the idea of precision and significant figures. Let's just say sig figs. Sig figs. When you are making measurements, you are limited by the accuracy of whatever kind of, or the precision of whatever kind of the thing you're measuring. Like if I'm using a ruler that only measures in whole numbers, and I'm trying to measure how big is something, you know, I can say, oh, it's about 2, definitely less than 3, more than 1. If I have something that measures in quarters, I can say, oh, it's like 2 1/4. You know, if I have something that measures in even finer things, you know, so when you write a number in math, if I write 3 or I write 3.0 or I write 3.00, those are all the same if I'm in math. But if I am in science, those are super different. This means I measured it, and the closest I could get is it's near 3. It's 3 plus or minus like 0.5. If I have 3.0, it means I measured it with a better ruler. And this is 3 plus or minus 0.05. If I measured it this, that means I even have got a better instrument to measure it. And this is like 3 plus or minus 0.005. Right, so the number of significant figures you're using is really important. And when you're taking measurements, we talked about, in order to deal with randomness, we're going to be taking multiple measurements and then averaging things. Like, so for like the height, for instance, you'll measure somebody's height, and maybe it's, in fact, we'll measure, X, Y, and Z. Let me think about, I need a calculator just to make life easier. Let's say I'm measuring whatever, and I measure it 38.5, I measure 39.4, and I measure it 39.3. And I want to get the average. And so I go into my calculator and I say, 38.5 plus 39.4 plus 39.3. Then I divide by 3, and I get 39.067, or actually 06666. These numbers here, that if this is science, is implying that these are real and that we measured it and those have accuracy up to there, which is not true. So that you can't do that. So the idea of sig figs, which I know that you learned in chemistry and we're going to be continuing using in this class, is when you do a calculation using measurements, what is the basic rule for the answer using sig figs?
It has to be the same number of sig figs.
Yeah, you are limited by your least accurate piece of data. So if each, here we have 3 sig figs, that means our answer has to be rounded to 3 sig figs. So this would be, 39.1 is my average, because this is going to be 3 sig figs, because my data is limited by 3 sig figs. Sig figs, significant figures. So if there's also a little thing I've put on there to like review it, as well as accuracy and precision you can look at. I just kind of wanted to float this out there for y'all. Okay. All right, so for the jumping lab, and I want you to notice there's 2 parts to the jumping lab. Today we are going to do kind of an initial thing. We're going to kind of talk about what the actual procedure is, look at some initial data that we have recorded from a smaller class. But next week, we're going to continue on looking at the analysis and looking at ways to use tools like Excel to work with larger data sets. So the jumping lab is going to be today, and there'll be like an initial analysis that we'll talk about, but we're going to continue with this same lab into the next week. So this doing the jumping lab. These are some little things that Tina and I recorded right when we went into shutdown, trying to like, this was like a while ago, trying to like show what things looked like. So I'm just going to play this for you right now and like do a few little comments, but this is kind of showing, from the lab procedure, how we actually got the data, because you're going to be using data that we got in another class, but I want you to make sure you see exactly how the data was gathered. So this is just going to be watching us on a little YouTube thing, and I'll comment as we go. Whoop. Wait, so something is missing here. Hold on. Man, I wonder if it's that. Okay, I think I need a. Dagnabbit. Yeah, maybe it's the captioning, but the Zoom is just being weird. All right. Here we go. All right, here you get to see what I looked like a year and a half ago. It's pretty similar. All right, so this first part is just going to talk about how we get the data. So this is the jumping lab. And in this lab, we're going to be taking a variety of measurements off of our subjects and then looking for correlations with their jumping height. So one of the measurements we're going to be taking is their height. Again, just talking about sources of variability, your height is going to be really different depending if you're wearing platform shoes or you're barefoot. So before you take anybody's height, you gotta make sure you don't got shoes on. Shoes. Another thing, some people, I don't have poofy hair, obviously. Some people have poofier hair. You want to make sure as you're measuring height that you compress down and you're actually getting their actual height and not the height. So here we have meter sticks taped on the wall. I'm gonna stand here straight and
Okay.
I'm gonna show parallel.
What was that?
Show parallel. Over underestimate.
Oh, yeah. So it's important that it's parallel or perpendicular to the ruler in the wall, because you could measure too high by doing this or too low by doing this. So you want to have it completely perpendicular. And these meter sticks are marked with millimeter tick marks. So in this case, we want to measure to the nearest millimeter. And then you want to record that in your lab notebook. And also don't forget that there are 2 meter sticks taped here. So any person in the lab is definitely going to be over 1 meter tall. And then we reach to the nearest millimeter here. So in this case, it could be 1.665 and then you can convert that over to meters.
And so we're going to continue, but while we're at here, I'll make a few other points about this kind of measurement. If we were doing this in person, I limited how many labs we're doing in person just to try to keep the logistics easier. But if we're doing this in person, we would have 3 different people doing the same measurement on the same person. And you actually would probably be surprised that people don't get the exact same number, because they push a little harder on the poofy hair or not, or the ruler is tilted slightly. Even if it's barely tilted at all, it might make the difference of a millimeter on the actual measurement on the stick. So it's not a bad idea to take a measurement multiple times and make sure it's the same or average the values if they're not. Another thing, when we do this in person, people don't realize there's 2 rulers there and they just read one of them and they'll say, oh, this person is 67.3 centimeters tall, because they're only reading off of the top meter stick instead of realizing that it's a meter stick on top of another meter stick. So this brings us to this idea. If if you got a number like this for somebody's height, what should you be thinking?
They're just looking at the second meter stick and not including first.
Or that something's wrong, something's way wrong, because they're not a leprechaun, right? 67 centimeters, that's about 2 feet tall, right? A meter is about 3 feet. This is about 2/3 of a meter. This is about 2 feet tall. So we have often what we call a sanity check. Different people call it different things. Sometimes people call it a dummy check. And I used to say that, and then I had students complain, they're calling me dummies. That's, everybody makes mistakes. I make mistakes all the time. I am constantly doing these little sanity checks on myself to make sure that, does my answer make sense? Is it completely ridiculous, or is it in the ballpark? If you measure the weight of a canary and you came out after all of your complicated work and it said that your canary weighed 37 tons, you'd say, okay, something's wrong. There is no way. I know this 37 tons makes no sense at all for the weight of a canary. The same way that 2 feet tall makes no sense for the height of a human being in our classroom. So whenever you take measurements or do calculations, please do this kind of sanity check. People will turn in like graphs in their jumping lab even, and they'll have weights for people where, or calf circumference. They'll mess up somewhere in their graph, and the calf circumferences will be like 4 centimeters. It's like, no, it's like, that would be like a, I don't know, like a stork or something, so you need to do this sanity check. Part of it is also people aren't as comfortable with metric units. If you grew up in Europe, you saw that somebody was 67 centimeters tall, you would immediately have like this gut sense of like, that makes no sense. Whereas in, United States, we use the weird imperial units. And if I say somebody is like 1 foot tall, you'd say that makes no sense. So in science classes, you gotta get an intuition for the metric units, right? A gram is somewhere around a jelly bean, right? A kilogram is around 2.2 pounds. A meter is around 3 feet. A liter is around a quart. Like, I know in Bio 110, they had you remember different body parts, trying like, centimeters about the width of my finger, a millimeters about the width of my fingernail. Go back to that. Use that for your sanity check. Your sanity checks only work if you have some sense of what the unit actually is. So please, as we go through the semester, make sure you get more and more of a intuition for what is a gram or a kilogram or a liter or a milliliter or a meter or a millimeter, because we'll be using those. And you can't really do this kind of more intuitive sanity check unless you have an intuition about what that unit actually is. All right, so blah blah blah, back to the latest YouTube star. All right, so social media influencers, David and Tina. In the actual lab, you would have more than one person take the same measurements, because even though it seems like a straightforward thing, there are so many slight variations, the exact angle of the meter stick, or just somebody's approximation of whether it's
or down 1 millimeter, that can actually lead to a different value. So to try to get at the true value, we take multiple measurements and we can then average them and then assume that that average of those different measurements is approaching our true. All right, so this next part is measuring the cap circumference. And again, here's another example where we need to bring in this idea of thinking about sources of variability before you actually do the experiment. Like, just like you have right-handed and left-handed people, there are people who are right-legged and left-legged, have a leg that they prefer. And they're gonna probably have more muscles on their leg that they prefer, so the calves are probably not exactly the same. So it actually is gonna be important to like acknowledge that before we start and then come up with some way to deal with that. And the way we'll deal with it today is we'll measure the calf circumference of their dominant leg. That would be the leg, like if you were told, go hop on one foot from this side of the room to the other side of the room, which leg do you hop on? And that is your dominant leg. So when your subject is getting ready for this, have them hop. See which leg they prefer, and then you want to measure that one. Also, I highly recommend if you know you're taking your shoes off for this lab, wear fun socks.
All right. And we're gonna measure it 3 times with 3 different people measuring the subject's cap circumference, and then you're gonna average that.
Right, and notice like in this thing, sources of variability, if someone was more on their toes versus flat-footed, it's really important that you have a consistent method for doing the measurement. You know, so as different people do the same measurement or you're measuring in different groups, you can compare. Like if some people were on their toes or wearing high heels, that would affect the calf circumference measurements. So having kind of this consistent methodology across the groups so we can actually combine all the data is important. Let me stop sharing. You know, obviously to measure the weight, we just have them stand on a scale. So we didn't figure that's straightforward enough that we didn't have to film that for you all. But this is how we get the data for the independent variables. You know, so in all the data, you're going to have data today that I'm going to give you. That's going to be from a single class. And then next week, we're going to have data from a larger group, actually across 3 classes to look at, see if trends we notice with the smaller class hold up. All of that was just taken this way, like you saw in this video. People measuring their height 3 times, averaging it, measuring their calf circumference 3 times, averaging it, measuring their weight. And then what's the other piece of data we need to do this experiment?
Wait,
Jump. Highly jump.
The jump itself. You know, and for the jump, there's also, it's worth thinking about what are sources of variability for the jump that people have talked about?
Injuries.
Injuries. So in general, we would exclude someone who has any injuries that are going to affect their ability to jump from being a subject. In any kind of experiment, you always have what are called exclusionary criteria. Like what are the criteria that are going to make somebody a bad subject for this experiment? So somebody who has some injury that is affecting their jump, that's probably going to have more of an effect than anything else. So let's not use them. What are other things, other sources of variability?
type of ground that is being jumped on.
Yeah, totally. You know, in this case, we're all going to be jumping on the linoleum in the lab, or the concrete outside. You'll see actually. What are other things?
Their
Is it-
attitude.
Attitude. I mean, that's huge. Actually, in sports psychology, that's it, visualizing. If you picture yourself doing it, and it makes a huge difference. When we do this in real life, what IRL or whatever they say, you convince people to really try, get out of your self-judgment of I look ridiculous or whatever, and just have fun with it and just try to jump as high as you can. Because if you're like, this is stupid, and try to jump versus like, all right, I got springs for legs, I'm gonna hit the roof, that makes a difference. So in fact, we had, again, when we had time to do the independent study, research studies, there was one group that took this particular lab and modified it to have these little affirmations of like, I feel like lead, I can't jump, like I'm tired, my limbs like feel so lethargic, versus like, I'm a great jumper, I'm made of springs or whatever, versus some like control thing of like, I had yogurt for breakfast or something. They had to say something, and they did find correlations between, having these positive jumping affirmations with jumping higher, as opposed to these negative jumping correlations with, so it really does. I mean, in our own classroom stuff, as well as in more of the sports psychology things, it makes a difference. So we always encourage people to jump with like enthusiasm. What other things are sources of variability?
Pain or muscle fatigue?
Yeah, fatigue, being tired, or it could be muscle fatigue because you've been running around, or it could just be central fatigue, like you didn't sleep enough. But that can affect things a lot. In fact, later on in the semester, we're going to look at those as separate things. Like, what does it mean to be tired? Like, I don't want to get out of bed, versus my muscles just aren't working anymore because I've just been using them a bunch. There's, and other things in addition to not sleeping, different drugs on board. If you just drank a Red Bull, or did you just drink a beer, that's going to make a difference probably in your athletic performance. There's lots of things. And then the mechanics of the jump, so the one thing we can control is trying our best to make sure everybody jumps using the same mechanics, the same arm swing and things like that. So what I'm going to show you now is the second video, which is just another, it's like 5 minutes, show you what the jump looks like. And once we finish with the jump, then what we're going to do is just look at what the data looks like and talk about kind of an initial attempt to like trying to analyze the data. And like I said, we're going to do this in much more depth on Tuesday next week, but we're going to do some initial analysis today. But first, we are going to watch an example of what the measurement of the actual jump looks like.
All right, so measure my height, my calf circumference multiple times, so we get hopefully as true a value as possible. We've also measured my weight standing on a scale. You all know how to do that. And now we're going to talk about our dependent variable in this whole experiment, the actual vertical jump height. A few things before we start that. Another source of variability is the actual mechanics of the jump itself. If you just kind of do that or whatever, it's going to make a big difference on how high you jump. And because we want to look across many subjects, we want to have a standard jump where everybody's doing the same mechanics, which I'll briefly show you. It's basically as described in your lab manual. You're standing vertically, your hands by your side, bend your knees, and then you're going to extend your knees as you swing your arms up. And you want to have your legs and your arms arms extending simultaneously so they both are at full extension at the same time. So there's this really nice kind of synergy that happens. And you also want to make sure you're using both arms. A lot of people have this tendency to like jump like that and just throw up one arm and they have their half of their body is just kind of paralyzed. So you want to have one straight, bending at your knees, and then in one smooth motion, float up with your arms going up, your legs straightening, and actually show how it's done. I'm gonna have my pencil here where I'm actually gonna be able to mark. Now, obviously, we want to see how high can I jump from my normal height. I don't care if a person is taller or shorter. You know, they're going to be able to mark the paper higher or lower depending on their height. That has nothing to do with their jump. So what I care about is where do they mark it if they're just standing on the ground? And then I'm going to be able to jump and mark it at the peak of my jump. And then I'll see what's that relative distance. And so I'll do that. This is my baseline. Top footed. Ready? And I want to, yeah, every time you jump, you're obviously not going to jump exactly the same height. So another thing we're going to do, just like we did multiple measurements for height and all, do multiple measurements. Okay, like that. And holding the pencil the exact same mark at the top of my jump. Ready, straight body, fat legs. Go up. There's the second jump. And I'll get ready. And one last time. And my lab partner, if I go in like this, my lab partner's got to say like, whoa, that wasn't it was nice to watch you jump. That wasn't a jump we can count because you didn't have to talk before. So as a person, you know, making sure the experiment is done correctly, you need that, you know, you don't want to throw away data just because it isn't what you thought it should be, but you don't want to take data if they actually do the procedure properly. That isn't. Okay, my third jump. And now I have 3 little marks up there. And now it's time to measure how high my vertical jump is. So we can see how it correlates with my height, my weight, my calf circumference, and some other things.
So next it's time to measure David's jumps here. So carefully, without falling off, you want to get out here. You use the metric system of any ruler that you have. And then, of course, it's not very handy for me to record this. I'm going to have to yell out the numbers for my lab partner to write down in the lab notebook. So I'm going to move from the baseline to the first mark here at the highest point. And it's going to be 47 centimeters and a half a centimeter. So 47.5 centimeters. 47.5. All right, second jump. 46.2 centimeters. And the third is 47.0 centimeters. Those are the 3 jumps that they can do.
All right. So, you know, those 2 little videos there are just to kind of give you a sense of how we actually got the data that you're going to be working with. You know, it actually is a fun lab to do, but again, like I said, in trying to, once we were told we could do hybrid stuff, which happened relatively late, I was like, let's just do the critical things, like the chemistry, like the blood and the EKG. Like, it's fun to jump around, but I don't think it's as critical to make a whole trip to campus just to jump around. So what we're gonna do now is talk about, let's assume you have all written your objective and your hypotheses, and then you've got your data. And you have your personal data, and then you put it in a spreadsheet in the front of the classroom like we did with the pH data. What's the next step? What's the next thing we're going to do? We've got the data from all these measurements, and you have your objective and your hypothesis.
You're gonna make graphs to see if they correlate.
So that's going to be part of it. Be a little more explicit, like to what end? What are we, what's the first real step in this?
We're gonna compare like the weight to the
Where's our
jump.
starting point to kind of focus us on what exactly we should be looking at?
See if the data supports your hypothesis.
Exactly. So, right, so when you are looking at something like this, first, check if hypothesis is supported by the data. That's going to be the first step. That is what I'm going to have you all be doing like over the weekend, is looking at an initial amount of data, initial data set, and just look at your hypothesis, not necessarily look at everything. Like the first step, but then second, check data for other interesting trends. So after you analyze the data and check to see if it supports your hypothesis or not, then you'll look at the rest. Let's say your hypothesis was just about calf, then your initial analysis is going to check, does calf circumference seem to predict vertical jump? But after you're done with that, you've got all the data. You might as well check to see if there's other interesting stories in there. So then you're going to check, check the rest of the variables. The reality is when people design experiments or do things, a lot of times the most interesting thing is something somebody never could have pulled out of their head in the first place. They have a hypothesis, they have a question, they go look at the data and realize like, whoa, there's some interesting things in here that I never even imagined. So it's important not to get tunnel vision and just look at your hypothesis. Like after you check your hypothesis, you also want to look deeper and see, okay, maybe my hypothesis isn't supported, but is there some other interesting story that this data has to tell? In the real world of science, people often do an experiment and what they were really looking for in the first place wasn't so interesting, but they noticed something else they never were even expecting. And then they follow that down a rabbit hole and find lots of really cool stuff that they would never have even thought to look for in the first place. So, the real process of science is being open to seeing things that you didn't expect, because this idea that you can like a priori predict anything that's interesting in the universe that's worth looking for is ridiculous. So what we're going to do now is go back to the sharing screen. It's 12:08. So here was this same page, doing the jumping lab. There are these videos. You've seen them. You could watch them again if you want. They're so this next thing, it says Fall 2012 Jumping Lab. So I am downloading this right here. Whenever you download data, these Excel sheets, make sure that you download them and open them up in Excel as its own program. If you are in fact, I can show you this. If you are here, I can do a preview where it looks like I'm seeing stuff, within the browser, but it's not the whole file. You can see partly, but don't trust that to be the file. What you need to do is download the file and then open it up in Excel proper. And then you know that you have, you're working with the right thing. So enable, oh, that, okay. Let's close this. Okay, here we go. All right, so here is this data. There's the sex, the weights in kilograms, the heights in centimeters, the calf circumferences, the BMIs, and then the jumps. Next week, we are going to use much larger data sets. We're actually going to use Excel in order to graph things out. But for this first part, I would like people just to do things manually, just to prove to it's a small number of numbers, and I want people to trust that they can graph things on paper. So at this point, can someone tell me their hypothesis? For this lab?
I'll go. I thought that of all those, height would be the best, would have the clearest relationship with with the height of someone's vertical jump.
And then what was the why for that?
I was not able to explain that well, but I thought just according to scale, a taller person should be able to jump higher in much the same way as a flea is a much better jumper than a human and can jump more proportionally, but we can actually jump higher than a flea can because we're just bigger, taller.
Although that has to do the flea, like you could say a flea and an ant are similar scale, but the ant and the flea have very different jumping. So I would say, longer, you'd probably want to be a little more grounded in something that you can say, like, longer limbs would have larger muscles that generate more force or something like that. Or the mechanics, if you can swing over a larger moment arm, you can generate more angular momentum or something like that. So I would say it's, saying height versus jump, height is going to be predictive is a good thing, but probably in your hypothesis, you'd want something a little more concrete than fleas, because there's things as big as fleas that don't jump much at all. So you'd want to, like, what is it about a flea that helps it jump even?
Okay.
I'm curious now. So let's say we want to check if John's hypothesis is supported by the data. What would be the way to take that bunch of numbers and analyze it to see if his hypothesis is supported?
You could graph out height versus jump and see if there's a direct correlation.
I'd want to make a scatter plot, some kind of scatter plot. If I'm going to check two variables and see if they're correlated, I do a scatter plot. Usually you have the independent on this. So this would be like the height. And this is usually the dependent on the Y. This is going to be the jump height. And then when I do this, I am going to want to have the data kind of fit on the page. It doesn't make, nobody is got a height of 0. If I said height goes from 0 to 200, all my data is going to be over here, and most of this is going to be dead space. So I want to do my axes spread out, like from the smallest height to the largest height. So that means I'm going to go back to the actual data. Okay. Going back to the actual data here. And I can say, okay, here are my heights. And for what this, I don't know why it's not working right. But I can say, okay, my smallest height is like 151. My largest height is going up to about 181. So if I go from 150 to 190, that is going to be a good range for the height. For the jumps go from, I don't know, like 14 up to 61. So that means when I am doing my graph, let's start at 150 here. When I look at my jump, I always have units. And because we're actually using this quantitatively, we're using this for analysis, make sure that you don't get sloppy. Your quadrille paper, make sure it's like, 1, 2, 3, 4, 5, 6. Whoop. Maybe each box is 2, 52, 54, 56, 58, 60. So when you're doing this, sometimes people get all kind of weird and like 100, and then this is going to be 175 here, and this is going to be 109. It's like, no, make sure that you're being consistent with how much one little box or one tick mark is in terms of the measurements. So if you're doing height versus jump, first thing is figure out how to do your axes, and then you just get the data. If I look at the data there, the first one there is got a height of 178, which is going to be here, and has a jump of 61, which is off of the, let's say it's up there. The next one has a height of 176, which is more here, and has a jump of 27.4, which is more here. So I'm going to start putting all of my data points. The next one has a height of 168 and has a jump of 30, basically 40, that's here. So each data point is just put in the dot that is that subject for their height and their weight. And then once you get all the dots, you can then kind of do a best fit line and see if, does it seem like there does seem to be a trend. The best fit line, you can do it mathematically. We'll talk about how to do that with Excel next week, but you can eyeball it. It's basically half the dots are above, half the dots are below it, or it's just kind of the center of gravity of all the dots. If I had something like this, this would support height being positively correlated with the jump. if I put all the dots on there. So a scatter plot, just take your data, one continuous variable and another continuous variable, put them in a scatter plot, make sure you have your axes scaled appropriately, and just see, is there a best fit line that seems to show something? You know, it might very well be that you get all of your dots and your best fit line is, there is no correlation. Right, that's perfectly fine answer as well. It's like, no, the data does not support my hypothesis. What if what's another hypothesis that people had?
Mine was a little bit of a combination of two. I said, I think that taller people with a BMI within the healthy range will jump the highest because they will more likely have the athletically ability to jump high as well as less weight to be moved.
So how would I analyze that? From what we've just been saying.
It could be similar, but instead of height, you would have BMI on the axis.
So not quite. You know, you still are looking for the correlation between the height and the jump, but we do have to bring in this other factor. How would we bring in
Would
this
you
other?
need like two separate graphs?
Actually, you wouldn't even.
You could just select for people among a certain group of all the people doing the test that have the same BMI, and then
Right,
use that
exactly.
as a smaller group.
So I would just look at the subset of the people that have healthy BMI. And then in that subset, now I could do their height versus their jump. Right? So that would do it for me. That would let me see that height as a predictor of jump height for people with a healthy BMI. Let's do that same graph we did for John, except instead of do it for the whole class, just for the subset of the class that has a healthy BMI. We might see a very different result. Does that make sense? What's another hypothesis that people came up with?
I'll say it. I'll say mine. This is my like third revision. I think you haven't approved this one, but I'll go ahead and say it anyways. So I believe there's a direct correlation between height and calf size and a higher vertical jump, but not with the body weight being a significant factor. I think the correlation will be directly related to calf circumference because calf circumference is related to muscle mass, which is due to an increase in strength.
All right, so if we wanted to look at calf circumference versus jump, how would we analyze? Let's see if the data supports that.
Calf circumference would be on your x-axis.
Yeah, exactly. It'd be just like the one with height versus jump, except we would look at calf on the x-axis and look to see if there's a correlation there. So if you're looking for calf, or if you were looking for weight or for height, it would all be similar, kind of scatter plot like we were showing. What if I was trying to see whether or not healthy or unhealthy BMI was correlated with the ability to jump? What kind of graph would I use to check for that?
You could still do a scatter plot. You just crunch two sets of the measurements to get BMI, right?
But so for this, a scatter plot is more when you have kind of a continuous number of values. And for this, we're going to look at two basic things, either healthy versus unhealthy.
Bar graph?
Yeah, this would make sense to do a bar graph. And my computer is completely spazzing. I can't see what you see. Can you see my whiteboard right now?
Yeah.
All right, so what I would do here, I could go back to that Excel spreadsheet with all the data and look at the people who have healthy BMIs, and I look at their jump. I would just take everybody who has a healthy BMI and take their jumps and average those. So I could just get average jump in centimeters for my healthy BMI people, and it's going to be something. Then I get all my other people who have unhealthy BMIs and average their heights, and that's going to be the average jump for the unhealthy BMI people. So this would just be a bar graph. So if I'm just comparing two categories, like healthy versus unhealthy BMI, then I would use a bar graph. Or if I was going to compare men's jump to women's jump, it would also be a bar graph. Just get the average jump for all the men and the average jump for all the women and put it in a bar graph. So those are the two basic tools that you have. And that, again, I do not analyze everything. You know, just, and if you have a multi-part hypothesis, just like one part of your hypothesis. You know, if you have, Holly had a few different parts, she could just analyze the calf or just one part or another part. So before Tuesday, I want people to look at the data that's on the module there and just do a simple graph of one sort or another and have a initial conclusion on whether or not the data supports your hypothesis. So what I would like people to do, if you look here on that module for the jumping lab, as we've just been saying, here it is. You know, it says submit PDF of initial jumping lab discussion. So for that, I just want you to submit your initial analysis based on one aspect of your hypothesis using this limited data. And then on Tuesday, we are going to much expand our analysis. We'll include a much larger data set, and we'll see how to use Excel to like crunch numbers much more easily. Because once you start getting larger data sets, then you don't want to do it by hand anymore.